All right, today we're going to talk a little bit about data screening. Data screening, one, it's not necessarily a multivariate topic, okay? Because you should be screening data with univariate tasks, with multivariate tasks, with whatever kind of data that you're doing. You probably should be screening it just to make sure it's accurate. Lots of issues come up. You may have set up your online survey incorrectly, like Qualtrics or something may have the numbers incorrect. If someone's actually typing in numbers, they may have typed it in incorrectly. You may get repeat numbers or doubles or things that you don't want in the data. So just to make sure your data is accurate. So data screening really could be retitled data accuracy or something like that. But on top of just screening data for mistakes and for errors and data entry or for problems with Qualtrics or something like that, you also want to screen for assumptions. Now, again, assumptions are not necessarily like the sexiest topics, right? Because they're just things that sort of we have to meet in order for stuff to work. But in order for us to properly identify or properly, really what I should say is properly interpret the outcomes of these analyses, we have to be able to show that the assumptions are met, at least reasonably so, because it's these assumptions that allow us to make those interpretations. So these are things like assuming that data are linear or continuous, normally distributed, right? Stuff like that. And some of the tests have additional requirements, things like homogeneity of variance and sphericity and other things like that we'll talk about as we go forward. But let's talk about some basics of data screening and sort of assumption checking, and then we'll move on to talk about other topics in the next section. One of the first things, and I sort of mentioned this a second ago, but one of the first things you really want to do when it comes to data screening is just check the data entry if possible. Now, if you have a relatively small data set, it's actually pretty easy. You can actually probably go through every entry. I know many people, researchers will have, if they're actually entering data, if you're using paper and pencil surveys or something, and somebody's actually entered the data into a spreadsheet, they'll oftentimes have somebody enter it or a pair of people enter, and then a different pair will go through and check. If that's possible, we'll go through and check every single entry. Now, if you have thousands or tens of thousands of data points, this is probably not super realistic because it can take far too long, far too many person hours to go through and check every single entry. So you want to make sure that you have some protocols in place to make sure that as data are being entered, they're being entered accurately. You want to be able to spot check, maybe do random checks of some of the data to make sure that you're catching everything and sort of see what kinds of mistakes are occurring. That way then you can screen for those. So one of the first steps is to just go through and ensure the data was entered correctly. Check each individual entry if you can. Makes sense if it's small, like I said. Can be too costly, so if it's really big, sometimes you can just run ranges. Have SPSS or R or whatever program you're using spit out to you the ranges of data just to make sure that you're getting things that make sense. Like if you're using a Likert scale and it's 1 to 7, and you're noticing some other numbers, 8s, 10s, or some other weird numbers in there, probably want to check that out, see what's going on. You also will get sometimes you'll get interesting things like your scale's 1 to 7, but you'll get some 9s or 99s. That's a 99 here. So that could be because you're specifying that 9 or 99 are missing values. So again, whether or not to leave missing blank or to add in codes that mean missing is another conversation that we'll talk about in a second. But you at least want to make sure that the numbers you're getting are in a range that you expect. Now, if they're all Likert scales, which means that they're all whole numbers, 1, 2, 3, 4, 5, 6, 7. If you're seeing values of like 1.2 or 7.4, I guess 7.4 is actually outside the range, but 5.5, so, you're getting weird decimal numbers, you probably want to check it out too. Something might have gone strange in there. Now, sometimes you might get some some decimal numbers on a Likert scale, depending on how you approach your data entry. For instance, if you have a scale that's like 1, 2, 4, 5, 6, 7, where this is like, disagree to agree or something, right? And it's a paper pencil test, and someone does this. Oh crap, I don't know if they circled the 5 or the 4. It looks like they're trying to circle 5, but they got some of the 4 in there. So sometimes, some might just enter this into, when they're entering, it might enter this in as 4.5, just because instead of leaving it blank or leaving it as unknown or something, they'll just substitute 4.5 in there because they don't know which one they circled. So again, this also goes back to sort of your setup and design of your surveys and questionnaires and things, because you want to make sure to try to avoid that as much as possible, not have numbers that are too close together. Instead of having them circle, maybe you have little things that fill in below each of the numbers. So I didn't do that very good. Below each number is the thing they fill in. But even then, I thought they're supposed to fill this in right as their answer. But sometimes, who knows, they might, fill in across 2 of them. So sometimes this is a solution. So, but again, you want to make sure, go through and check to see if the numbers you're getting are numbers that you should be getting. You'll find sometimes as people enter data in, or as I found a lot of times too, when setting up an online survey, you'll get this a lot too, where as you're adding in a question, this happens in Qualtrics. I know it happens in other platforms too. I've seen it in Red Hat and I've seen it in SurveyMonkey, where as you're putting a questionnaire in, if you try to add in choices or you're trying to change a question, it sometimes does weird things with the numbering. Instead of keeping the numbers linear, like from like the top to bottom going, or left to right going, like 1 to 7 or whatever, you'll get like, it's like 1, 7, 4, 2, 3. Like it actually goes in an odd order depending on how you added them in. So it's also a good idea to go through and check your surveys, your actual platforms you're using, Qualtrics, SurveyMonkey, Red Hat, whatever. We used to use one called Psych surveys a long time ago, to make sure that the numbers are actually getting the actual numeric values for your choices are what you think they're supposed to be. Because sometimes they're not. But beyond just checking your data, you need to check assumptions. So whenever I hear assumptions, I always have this very negative connotation with assumptions, because whenever you assume, you make an ass out of you and me. Right? That's the phrase. You make whenever you assume, you make an ass out of you and me. So I always feel like, wait, are we not supposed to assume? Isn't assuming bad? And I remember this is from my 7th grade or something geometry teacher, that you can't just assume things. You had to show proofs, right? Well, when it comes to statistics and our interpretation of outcomes from analyses, we actually have to make some assumptions about the data in order for those analyses to make sense, to be interpretable in the correct way. Everything we're talking about in here, with the exception of logistic regression, for the most part, is based in some way around a general linear model. Even the factor analysis is based somewhat on like a canonical correlation kind of approach, where we are still assuming that the values, the data we're using, are linear, normally distributed, continuously scored. The same kind of assumptions that we do in a general linear model. Like I said, logistic regression is the exception, but it's only a slight exception, because there's a linking factor, linkage that we use to convert it over from non-normal to normal, and then the rest of it applies just like this. So in general, most everything we're doing is connected to, in some way or another, the general linear model. Well, what does it assume? The general linear model, linear, right, assumes a normally distributed sampling distribution. So this is one of the biggest criticisms of the general linear model, is that it has to be linear, it has to be normally distributed. Not lots of things are. So if your data do not fit that mold, then and the assumption doesn't make sense, then you're probably not going to use these kinds of models. I mentioned that because I had an interesting, when I first got hired, there was a faculty member here who I will not name, out of respect, I guess, that I got hired. It was like my first day, sat down in my office, and this person had an office that was, close to across from me in the hallway. They walked in, they were like, you know that the normal distribution theory is bullshit, right? I'm like, what? What do you mean? He's like, she said, yeah, it's totally useless. Really? I mean, there's a lot of stuff built on the idea of a general linear model. And we went back and forth, and he was in a particular field that's super useful for. So he didn't find much use for general linear model kind of statistics, and he, I guess, took it to heart to come and tell me that everything that I had learned and built my entire PhD on was completely worthless. That's how I got welcomed into the department. Oh, it's awesome. But it's fine. I got thick skin. The kinds of data and analyses that this particular person used, so specialized, so specific that nobody uses it except for a handful of people. So whatever, I don't care. Everyone uses this stuff. I mean, this stuff is like very widely used. You just have to know, I guess my point of this is, don't be so rigid in your thinking about how one thing works and one thing doesn't. It may work for you, it may not. That's fine. But there's always ways to figure out what does work for your data, and be flexible. Don't be so rigid that you have to use ANOVA, that you have to use MANOVA, that you have to use these kinds of models. Know when it works, know when it doesn't, and use the appropriate model for your data. So we're assuming that the kind of data that we're going to be using, that you're going to be using, at least you have the choice to use these kinds of models. But if you don't, then don't use it. It's fine. You're not gonna hurt my feelings. We assume this normally distributed sampling distribution thing, and most of the time people really get stuck on this to think of it at a very specific level, which is that not just the sampling distribution, but that the distribution of the scores have to be normal. And that's actually not the case. So your actual distribution of scores will likely probably never be actually normal unless you have just a massive data set. Okay, so if you have, you have thousands and thousands and thousands of cases, yeah, it'll probably normalize. But that's not even really the assumption. It's the assumption is that the sampling distribution will be normal. So what does that mean? Well, this is typically met with either a large N or by assuming the population is normally distributed. So if I can assume one of those two things, so if I'm told, if I know the data that I'm collecting is coming from a population that's normal, then I don't have to worry about it, period. I don't have to worry about any of this stuff, okay? If I don't know that, which often we don't, we oftentimes don't know a lot about the population distribution, which is why we're doing a study in the first place. But if that's true, then you just need to make sure you have a large enough N. And what's large enough? Depends on the study, depends on the kinds of analysis. But say for a typical ANOVA, you have to have, I think, degrees of freedom for error that are more than 20 or something. We're not talking about huge amounts of data. For ANOVA, it gets a little bigger because it's multivariate. And the more things you're trying to estimate, the more data you need. But usually it's not that ridiculous. When you get into structural equation modeling stuff that's in, say, Psy524, or even with exploratory factor analysis, those can blow up kind of huge because of the kind of model it is. You actually have to have more data in order to sort of meet the assumption. Okay, so what happens when you have a smaller N? Well, then we start to check the individual scores for some semblance of normality. We want to look for severe violations of skewness or kurtosis or outliers. Skewness being, that it has long tails. Kurtosis, again, has to do with sort of being skinny or too flat. And we want to look for things like outliers, because outliers really represent something that doesn't really belong there. We'll come back to that in a second, too. So when thinking about normality, we usually think about, we often focus on skewness, because skewness tends to have the most impact on our data when it comes to things like ANOVAs, t-tests, that kind of stuff. Now, why is that? Well, skewness, hopefully you remember, hopefully you remember, skewness has to do with you either have, a tail that's too long that way or one that's too long this way, okay? And the skewness always sort of points in the direction of the tail. This is pointing positively, this is pointing negatively, so this is positive skewness, that's negative skewness. Why do we care about skewness when it comes to, skewness isn't good when you have a normal distribution theory kind of test. Well, let's think about why. So if this, this is somehow the center, let's see, this is the, here's our mode, right? Here's our mode in the center of both of these. What happens is the tail, because of the way that a mean is computed, it's actually going to be pulled this way. So our actual mean is going to be a bit higher, a bit lower in this case towards the negative. It's going to be pulled a bit higher in this case towards the positive. Right? These high numbers at the end are going to pull the means in the direction of the tails. Anything that affects the mean, anything that's going to change the mean or pull it out of place is going to wreak some havoc on an ANOVA, on a t-test, that kind of stuff. But here's the thing. It does mess with things. But let's say I have group 1 and group 2, and we're trying to compare them at t-test or something. The fear is that, let's say group 1 is normally distributed, group 2 is skewed, and we get a mean difference where this means for group 1, and this mean gets pulled up here for group 2. It's not a startling difference. Let's move this over just a hair. Actually, it looks like it lines up. Okay. So this mean here lines up with the mode there, right? It looks like, right near the sort of top of the hump. But we're getting this difference because this mean gets pulled upwards away because of the skewness. Well, it's possible that we could get a significant difference between these two means simply because this one's skewed. Whatever happened to group 2 didn't actually change them. It didn't actually do much. It's just that it may have affected only a couple people out here in the tails, right? That pulled the mean up. The majority of people weren't affected at all by the treatment in this group. And the significant difference we have is due to some bias introduced by the skewness. Right? So skewness can mess with the means, therefore it messes with everything. Right? It can actually cause some bias. But so everyone sort of worries about this sort of scenario. It's also just as likely, though, that if the groups are randomly distributed, if we randomly assign people to the different groups, that this group will also be skewed, and it's going to account for that. So this, mean will also be pulled upwards. So we're likely not to get any difference at all, or if there is a difference, like this group is different, the whole thing will move up. We'll get a significant difference, even though they're both skewed. So sometimes skewness can be a problem, but it also can be sort of washed out by the fact that it's going to affect the groups sort of the same. So it's not this all-encompassing, like, oh, you have skewness, you're screwed kind of a thing. There's some more things you got to think about and look at, and if you have enough data, this really doesn't matter anyway. So what we're going to do in this class is we're looking at something like SPSS, we're looking at skewness, we're trying to do some data screening. SPSS is going to spit out for us a skewness statistic. It's going to give you a value of skewness, which by itself is not super useful, but it will also give you a standard error for skewness, which is calculated here. It's just the square root of 6 over n, and the 6 is constant. It's just based on sample size. And when you divide those two numbers, the skewness statistic that you get and the skewness standard error, you get a z for skewness. Then we can actually look at to see, is the absolute value of that skewness greater than 3.2, 3.3, some in that ballpark. And the reason why it's 3.2 or 3.3 is that corresponds to like 99% of a z-score distribution. Okay, so there's a particular reason why it's 3.2. You're basically saying that your skewness is outside like 99% of the values you would expect for skewness in a normally distributed distribution. So it is significantly skewed. It's outside of what we normally expect. It's in like a 1% range. We can do the same thing for kurtosis. Kurtosis, you also get a kurtosis statistic, which again is sort of how peaked your data are. And I think I talked about that a little bit in the last lecture, but usually a normal distribution is a sort of bell curve, right? Well, it could be either a leptokurtic, where you start to get these really flat tails and a spiky sort of distribution like this. Not that spiky, but all right. Well, this is sort of leptokurtic. It becomes too homogeneous. There's not very much spread. Everybody's right around the middle. Or you can have something called platykurtic, which there's barely any central tendency at all, right? There's much more spread. There's not a whole lot of central tendency. Okay, so this is leptokurtic. Kurtic. We've also seen as leptokurtotic. This is platykurtic. Also seen as platykurtotic, but just too many syllables. Leptokurtic, platykurtic. I always think about platy sounds like flat, and that really was going on here. That's more flat. Lepto sort of sounds like leaping, up in the air. So you got leptokurtic, platykurtic distributions, and what we can get is a skewness. A kurtosis statistic, which will be positive or negative, and maybe it's positive when it gets more lepto and negative when it gets more platy. And you can, it'll give you a standard error for kurtosis, and you can divide those two and also get a z-score. Again, if it falls outside, your absolute value of that falls outside of 3.2, then it's significantly kurtotic. Okay. For most statistics, the skewness assumption is more important than kurtosis. So skewness affects the mean, kurtosis affects the standard deviation or the standard error, or the within groups variance. So that's why they both have an impact. Because if you're increasing the mean, you could be artificially increasing the test, getting significance. But if you're artificially sort of squeezing in, if the data are very homogeneous and very low standard deviation, when you're dividing by the within groups variance or standard deviation, standard error, you'd be getting significant tests also sort of with bias, right? You might be getting significance when you really shouldn't be. So both of those things can affect the test, which is why it's important to have shapes that are pretty much normally distributed, right? Symmetric, not skewed, not too leptokurtic or too platykurtic. You want it sort of right in the middle. And again, most of this stuff doesn't matter if you have enough people. Once you sort of get, into the 20, 30, 40, people in your sample or in your, per samples or something, most of this stuff's not going to matter because you're going to have a normally distributed sampling distribution, and that's going to sort of circumvents a lot of the problems we have with some of these distributional problems. So here just I drew these out a little bit, but here's an idea. Normal distribution, right, symmetric. You got positive skewness pointing towards the right. You oftentimes will have people tell you, we'll call this right skewed and left skewed, which is also fine. Pointing to the right, pointing to the left. The main thing you want to get is that it's the skewness is describing the tail, not the hump. This is where most people are. The tail is where the skewness is happening. These are few scores that are extreme on the low end. These are a few scores that are extreme on the high end. Here you got positive kurtosis, this extremely peaked. You see how skinny this is relative to this. And this is extremely negative. I mean, not only is it flat, it's actually going the other direction. You're actually having more people on the tails than you do in the middle, which seems like a pretty strange distribution, but that's where you get negative kurtosis. So what do I mean by sampling distribution? What am I even talking about? Because it may have been some time since talking about this stuff. Everything that we're doing in here, right? In here, in 320, 485 US, most likely, and in here, they're all types of inferential statistics. Inferential. We're trying to infer. What are we inferring? With inferential statistics, you have a population like this, right? Population. And from that population, we're going to sample, right? We're going to do some sampling technique, which is more like a 321 or a 692 if you're taking the research methods class in the grad program. This is all about the research methods, like how you get the sample is outside of this class, but some kind of sampling down to some sample, right? Which is dramatically smaller than the population, right? This could be 20 people. This could be 20 million people. Okay, so population big, sample small. We do everything here. This is like where all the magic happens, right? We do everything with our sample. We, manipulate them. We split them up into groups. We do stuff to one group and not the other group. We have, placebo groups and treatment groups. All this stuff happens down here. So the whole point of doing all this stuff and messing around with the sample is so that we can actually then go back this way. Much better. And infer meaning. So we want to do stuff with the sample so that we can make inferences back to the population. So it's this whole thing. We have a population that we can't really touch, at least not as a whole. So we take people out of the population to a sample. We do that randomly. We do that with lots of complex sampling techniques. We do stuff to the sample and we come to some conclusions. Hey, if I give this group this drug and this group placebo, we get a difference. So the drug's probably working. We do something like that. So that we can say, hey, if we did that with everyone in the population, we infer meaning back to the population, this drug, this treatment, this difference likely reflects a true difference back up in the population, right? So sampling, so we actually make inferences. So this whole inferential statistic thing is all about this process. We want to make inferences back to the population. All right. So what does that have to do with this sampling distribution thing I'm talking about? Well, somebody figured out that if you have a large population of people like this, here's my population. Okay. Let's see if I can get it to come out a little darker. Okay. Here's my population. Population has some mean, usually referred to as mu. Okay, mu. And it's got some sort of distributional properties like the standard deviation, oftentimes we refer to as like lowercase sigma. These are the population values that we're working with. This is what's going on in the population. The problem is we don't know this, and we don't know this. Right? They exist in the population, but the population is huge. So we're talking about if we're interested in CSUN students, right? This is my population up here, right? I have a population of CSUN students. It's a huge population that likely by the time we started sampling or started to study the entire population, people have graduated and new people would come in. The population would have changed by the time we actually got through trying to test everyone or survey everyone or do some kind of experimentation with everyone. So this is, for the most part, sort of untouchable in its whole, like, as a whole population. What do we typically do? Well, we take samples. Take a sample. So of this large population, I'm going to take a sample. I'm going to use it even in a different color. We take a sample out of there. We say, look, I'm going to pull this sample out, and it's going to have its mean, group of sample 1. Okay, so sample 1 has its own mean, and if we just took it directly from the population, it's likely to be fairly close to the mean of the population. If I did this over and over again, I would expect to find lots and lots of samples, all close to the population mean. Maybe that's what we expect, right? They're gonna be floating in and around all right here. You're gonna get occasionally some extreme ones that are out towards the tails, but most everyone are going to fall really close to here, right? Because that's where the population mean is. This is where the most people in the population are scoring, is where they exist. So we just expect lots and lots of distributions all to fall in here somewhere, right? And I'll just say like this is going to be for an infinite number of them. We're just going to keep doing it an infinite number of times. We're going to have a bunch of these things. In the end, we're going to get a distribution of those sample means that's going to be far skinnier. So here's our population, this big fat population up here. Our samples are going to be, each of our samples are going to be much tighter around the middle, because as we take multiple people, remember these are individual scores up here, individual people spreading out. These are groups. Group means are not going to spread out as far as our individual scores are. So down here, we're not going to have this funny thing that's going to be called mu sub x bar. So it's like a population mean, but it's based around the sample means. Right? So it's mu sub x bar. You may see this also as I'm using x bar, but x bar and m are the same thing, or m of x are the same thing. So you may have seen this as mu sub m, which is referring to the mean of the sampling distribution. So there's layers here. You have the population sort of above this line, right? This is the population. Here you have actual samples. And then down here you actually have what's called a sampling distribution. This is how do the samples pulled from the same population, how do they distribute out in a distribution? We'd expect there to also be some spread here. This is oftentimes called also like sigma sub x bar, right? For the reflected, it's not this, but it's close to it or something like that. Not actually close to it, it's gonna be smaller, but the x bar refers to the fact that this is based on the samples and sample means and not based on the scores. This is based on population of scores. This is based on our sample means. And you oftentimes will see this too written out as just S sub x bar to refer to the fact that it's sort of sampling. So whenever you see a sigma or an S, right, we're referring to standard deviation. That's referring to the scores. The scores, the S is usually referring to the scores in a single distribution. So the S here refers to, the spread in each sample, where the sigma refers to the population. Down here, this S, whenever you see sigma sub x bar or S sub x bar, we're not talking about standard deviation anymore. We're talking about standard error. Standard error is the distribution of means across multiple samples. This tells me how far means distribute out, where sigma or S tells me how far scores distribute out. Sigma in the population, S in the sample. So standard error, and the reason why you see both sigma sub x bar and S sub x bar is because most people don't do this process. We don't take, an infinite number or a high number of samples over and over again. Who's got the time for that, right? Who's got time to pull multiple samples? I want to pull one, maybe two, maybe three samples out of the population and do stuff with them. I don't need to do this over and over again every time I want to do a study. So instead, someone figured out that, hey, we can actually estimate sigma sub x bar by simply taking sigma, if we know it, the population standard deviation, dividing it by the square root of the n, whatever sample size we're pulling out. This is 25, for instance. We're going to divide by the square root of 25. So we can directly compute the standard error by simply dividing our standard deviation from our population by the square root of the sample size we're going to use in our actual sample. Okay? What if we don't know sigma? We don't know, sometimes we don't know the population value. Well, the same thing applies. I have S sub x bar, which means I take the S from my sample, just that we get from actually pulling out a sample that we're going to use. We divide that by the square root of n, and we can actually get our standard error based on the sample standard deviation. These are better, more reliable, right? The sigmas are because they're directly from the population. We don't have to make an inference about it. we just have it. They're there. This works in some cases, like if you're dealing with intelligence testing, for instance. We know that the population of IQ scores is normally distributed with a mean of 100, standard deviation of 15. So we actually know the population for IQ scores. We don't actually need to compute it like this. We can actually use the population value. Most other cases, we're going to rely on the sample value, and that changes everything from when I have this. I'm going to do a z-test because I know the standard deviation from the population, so I can do a z. When I don't, I'm going to end up using the sample-based one and do a t-test. All right, so the t adjusts for the fact that s is an estimate of sigma. Anyway, we can go on and on and talk about this, but I wanted to take this brief little aside and just remind you, when we're talking about sampling distribution of the mean, what is that even talking about? And how does this apply back to everything we're talking about here? Okay. Most of the time, the assumption of normality isn't at the individual sample. It's not here. This is not where we're assuming normality. We're assuming normality here. All right, so this is where we assume normality at the level of the sampling distribution. And there's two ways to get us there. Two ways where we can feel satisfied that this distribution is normal. One, easiest way, is if we know the population is normal. If this is normally distributed, this will be normally distributed. Okay, that's it. Okay. The other way, if we don't know what this distribution looks like, which oftentimes we don't, if we don't know what this distribution looks like, then we can at least take a large enough sample, make sure these samples are large enough that this will turn out to be normally distributed. Right? That's sort of how that works. Okay, so this is normally distributed because either this is normal or the sample you took out is large enough, and that large enough is usually 20, depending on what book. I've seen it 20, I've seen it 25, and I've seen it 30. But anything above 30 for sure, whether or not it's 20 or 25 or whatever, depends on the book. But 20, but by the time you get to about 20, it's pretty good. Here, I will show you an example of how the size of the sample impacts this. Okay, give me 1 second. All right, so this is you can see the link up at the top if you want to check this out. This online stats book. I just like this because it's a pretty easy demonstration. And we sort of switched over to sort of Khan Academy style. You just hear my voice and you don't see me. But what does this do? So up here at the top, we have a population identified. It is normally distributed. So over here, there's different things I can do where I'm taking different things. This is how many times you want it sampled. Down here, I can decide what size do I want it. So right now, this is just an n size 5. Okay. So if I do that, if I say animate, it's going to drop 5 scores. So this part here, right, is the scores being pulled from this distribution, and then it calculates the mean of those 5 scores and drops the mean down here. Okay, so this is just 5 scores. And do it again, it drops another mean. Okay, do it again, drop another mean. Now look at it, it's going to pull over here. So we had a couple extremes, so it pulled the mean over a little bit. So let's say if I just to speed things up, that's 5 more distributions, 5 more, 5 more. All right, just keep doing this over and over again. Let's say I do it 10,000 times. Say I do it 100,000 times. What you see is because the population is normally distributed, even with a small sample size 5, this distribution of means is normal. Okay, so I don't have to worry about whether or not my sample is normally distributed. It matters that this is, and as long as I have a normal population, this will be normal. All right, great. most of the time we don't know what this is. So let's say this is instead, clear all that up. Let's say instead of normal, it's skewed. There's a skew distribution. So this population is actually skewed. So again, most of the time we don't know it, but let's say this distribution is actually skewed. And so now I'm worried, oh, okay, well, there's probably gonna be a problem here. So let's say I leave it at n equals 5. And I just animate one so you can see what it looks like. So it's pulling people from this population. It's going to pull, most people are going to come from where the hump is, where the mode is in the population. So you're going to get a lot down here. These scores are going to be really extremes because they're coming from the tails of the population. But even then, even though we got this one extreme, the mean is pulled towards it, but not as far as the actual tail. This actual outlying score, it's not outlying, but extreme score. So again, let's skip all that and let's say I do this 10,000 times. 10,000 times, even with the sample size 5, the sampling distribution of the mean is much more normal than the population, right? This is extremely skewed. This has a little bit of skewness on this side. So it's not quite symmetric. It is leaning where you got a little slight skewness to the right-hand side. That's because we use 5 people. So with 5 people, we're going to have a non-normal sampling distribution. All right, what if I switch it to 10 even? Let's look at 10,000 times. Still a little teensy-weensy bit skewed. The right-hand side is a little bit longer than the left-hand side, right? Okay. Let's switch over to 20. Once I get to 20, you can maybe see a teensy tiny little bitty thing right there. For the most part, that's pretty normalized compared to how extreme this one is. This is very, very normal. So usually when you get to 20, it's pretty normal. About 25, normal. Okay, no more skewness. Once you get to about 25, the skewness in the sampling distribution goes away. This is one of the reasons why, as long as we have enough people, we can be sure that the sampling distribution of means is normal, and we can do all of our tests, t-tests, and OS, all those things. Let's look at one more thing. That's great if it's normally distributed. What if it's something like bimodal or something like that? Weird like this. We have a hump here, and then maybe another hump down there. Like our population actually look like this or something. This is another way in which the population could be non-normal, right? Does it actually fix it then? Right? So let's go back to 5 again. 10,000. So here's the interesting part. You're going to get points from both distributions, but you'll see the means are going to sort of fall somewhere in the middle of the two humps. Okay, so let's do it again. Animate. So you're going to keep getting values like that. Let's do it 10,000 times. Now, not the prettiest normal distribution you've ever seen, but hey, that looks a hell of a lot more normal than the population it came from, right? What if I move this to, let's go to 20, 10,000, normal distribution. So even when the population is bimodal, right, we're seeing a normal sampling distribution. This is the distribution of all the means from all the samples taken from this population. And if I did it 10,000 times with 20 people per sample, you get a pretty normal sampling distribution. What if I go to 25? It's going to be a little bit skinnier, but should be even more normal. Okay. Nice symmetric normal distribution. All right, so hopefully that helps. So going back to all this mess, right? We don't have to have a normal, our sample here, like this is our sample. That doesn't have to be normal. I just have to have enough people in the sample to guarantee that the sampling distribution of means will be normal so that our estimates of our standard errors will be accurate. Okay. So when we talk about normal distribution, we're not talking about here, we're talking about down here. Now, what happens if you have values that are under 20? Like if you have a sample that's say 15 or 10 or something, well, then you might want to look at to see if it's normal or not, because that'll give you some idea of how normal the population is, which is why we start to inspect it at that point. But otherwise, make sure you have enough people and this is not a problem, or make sure you're working with a population you know is normally distributed. All right, let's talk about outliers. So related to the distribution, normal, skewed, all that stuff, outliers relate because sometimes skewness is not really skewness. It could be just you have an outlier that's pulling the tail out. And sometimes things are outliers because they're in that skewness tail. So outliers and skewness sort of go hand in hand, and sometimes can be tough. You got to sort of check them both out simultaneously. Let's see what outliers are more generally. Like I have the data that should not be. These are data points that don't really fit with your data. Now that could be for a number of reasons. You can have data not fit mathematically, right? They're larger, they don't fit in the distribution, they don't sort of distribute out like everybody else does. But that's not the only way. That's the way most people sort of think about outliers. But an outlier could be someone just that wasn't supposed to be in the data set. You're targeting males age, between ages 20 and 25. That's your sample you're looking for. And you get a female. A female is an outlier. They don't belong in there. You get a male who's 30. Well, that's an outlier. Regardless of how they score, regardless of where they are in the distribution of your scores and your outcome, the person is an outlier because they don't really belong. They are not part of the sample or the population you're intending. Okay. Often viewed graphically as a point that sits outside of the distribution, but potentially detrimental because we're not really sure what kind of effect it's having on our estimates. It can affect the mean by pulling it, in one way or the other in terms of the tail. It could also impact the standard deviation, standard errors of our estimates, right? The within groups variance for ANOVA by adding to that variance by being sort of different or far out in the distribution. You can actually make the variance seem larger than it's supposed to be. Anyway, the outliers are a potential problem. They shouldn't be there, and we got to figure what to do with them. You could think of univariate examples of outliers. I'll show you examples of brains and ARC here in a second. Anytime you have issues where you have extreme values, the first thing you want to check to make sure that the data was coded correctly, because you could have something like, again, with Likert scales, you could have meant to put a 7 and then someone put a 77 by accident or something. So that could represent the extreme outlier some way. There's two ways of looking at outliers. A data point represents an outlier if it is disconnected, right? Or if it has an extreme value, again, this sort of 3.2, 3.3 z-score value. If it has a large z, then it's actually different than like 99% of the rest of the distribution. If there is a concern, you should run the data with and without the outlier to see if it actually influences your outcome. So you could do an ANOVA, and you do it with the outlier in and with it out. If the outcome changes dramatically, like it's significant with and not without, well, then that score is having an undue effect on your outcome and probably should be removed. It's having too much influence. Let's take a look at brains in ARC. All right, this is ARC. It's a very simple, very overly simplistic program. I like it because it does a couple things that other programs don't do. Even in R so far, I haven't found a package that does anything similar. You can see this is actually, it's been around for a little while. It's very text-based, very simplistic. But here's the cool thing that it can do. So let's go in here. I'm going to load up a data file. The one we're looking for is brains. Okay, so there's brains. I'm going to do a plot of body weight to brain weight. Down here you see there's the body weight is then regressed onto the brain weight of an animal. So these are just a bunch of animals. And we're taking their body weight and their brain weight. You got some extreme outliers here, right? And most everyone seems to be down here. If I fit just a regression line, ordinary least squares, I'm going to put that to 1. That just fits a regression line out there. You can see it fits pretty well. The data down at the bottom, it's going sort of right through there. Those are kind of hard to see because it's so squished down there, but there's lots of these that seem not to fit very well. Like this one, these ones seem not to fit. What kind of animals do you think would have massive body weights and brain weights that would be these extremes? Think about that for a sec. Looking at these extreme scores right here, we might be able to figure out what they are by highlight them. Oh, that's an African elephant. All right, that makes sense. Huge animal, huge brain. Probably why they're an outlying score. Okay, what about over here? The Asian elephant. All right, so what if we're thinking, all right, I want to plot these animals out and get an idea of how much their body weight and brain weight relate to each other, but these elephants that we have are sort of throwing things out. These are outliers because not quite fitting with the rest of this distribution down here. So I can actually go through and delete those selections from the data set. And I can rescale the plot. Now it looks like that. Now we're looking like something a little better. Notice that the regression line has come down quite a bit. When before the elephants were pulling it up much steeper. This is now the regression line is a little lower, but we still got some interesting things going on. Then we got this one over here. So this particular animal's got a fairly small body weight, lowish body weight, but a high brain weight. What could that be? Big brain, relatively small body. Well, it's humans. So humans here may actually be throwing a wrench in the works as well, because it's a pretty stark outlier. They're not following along this distribution. And in just a second, I'll give a name to some of these qualities of where they are lining up. But for now, just look, whatever this going on with this human, their body weight and brain weight is not quite matching up. So again, I can delete that selection, go back here, rescale the plot. Now it's starting to adjust again a little more. The rest of these are looking pretty good. There is some some things out here where there's probably some monkeys that have grace. Yeah, that's pretty good. These are probably a donkey and a gorilla. So again, you're talking about animals that have higher than average sort of brain weights relative to their body weight. Down here, it's the other way around. You got a cow, high body weight, sort of brain weight is not quite matching their body weight. Horse, giraffe, okay, makes sense. So you're starting to see what some of these are. I'll do one at a time. Baboon. Yeah, so all the monkeys are going to fall on this side. They have lower body weights but larger brain weights. You got deer, rabbit, raccoon. Anyway, you get the idea. This is sort of what's nice about the interactiveness of this program is just really cool. And that's why I like sort of using it for demonstration purposes and stuff. So we just looked at brains and ARC, and we were looking at I didn't necessarily go through and look at it as this Z-score above 3.3. I was looking at, look, it didn't seem like they were disconnected from the rest of the distribution. It seemed like they were not sort of lining up or following along with the rest of the distribution. They seemed sort of like they didn't really belong with the other points in the distribution. And that's really when what defines an outlier. We can actually describe the impact an outlier score might have on a regression equation by looking at these different points. So right now we're talking about regression and how, just like with the brains and ARC, and how points can actually change the regression line up or down. If a single point can have that much influence on changing the slope, then that's probably not good. It's probably it has an undue influence. And the way we actually describe that is leverage, just like with it means what you think it means, leverage, like in physics and things. But we're using it to here to talk about how far the point is away from the other points. So if you think about an imagined sort of center of the points, we can think about, if I have a bunch of points, let's say like this. It's got a regression line going through it like that. If I have a point that is, if I think about this as being the center, I'll put the center here, the center of those points. A point that is far away from the center in any direction, really, right? It's going to have high leverage. So a point out here is going to have a lot of leverage. But because it's lined up with the other points, it falls on the regression line, it's going to have very little influence, okay? Because it's not going to change this slope. It's actually lining up nicely. Even though it's far away, it's high on both the X and Y axes. I should probably label those, okay? Whatever they are, it's actually high up there. Now, discrepancy has to do with the pattern of points. A point is discrepant if it goes against those points. So here's a discrepant point. Okay, so it's actually not lining up on the line. This point has more leverage. This point is more discrepant, but this point's probably going to have more impact on the slope than this one does. Actually, this one's going to have very little impact on the slope. This one's going to have more of an influence because it's not lining up. Because when the line is trying to account for errors and it's trying to minimize the amount of squared errors between our line and the point, right? It's trying to minimize the residuals. Because it's trying to minimize residuals, it's going to try to do all it can to take a very large residual like this one and correct for it. So it's likely going to pull this down and lower the slope to try to account to make this this square residual smaller. So when you have two things together, when a point has high leverage and is discrepant, then it's going to influence the regression line. It's going to actually change the slope one way or the other to pull it to try to account for this large error. All right, so leverage, distance, and discrepancy has to do with how lined up it is. How does it follow the pattern or not? You need both of those things in order to get some influence, right? A data point has to be discrepant and it has to have some leverage in order to sort of pull the regression equation one way or the other, okay? So we call the change in the slope, that's the influence. So it's calculated as a combination of leverage and discrepancy. Both of those things together create influence. And here's some examples of that. So here you have high leverage, low discrepancy, right? So it's far away, but still in the same pattern. Here's high leverage and high discrepancy. So the pattern's going this way. This is going to pull the line. It's going to reverse it. It's going to go from a positive slope to a negative slope just to try to account for that one point. This one's got lower, it's still highly discrepant, but it's got lower leverage because it's starting to come in and be a little closer to the data. So it's not quite as discrepant. So it's going to have some influence, but not as high as this one. This one's going to have the most influence of those three examples. All right, we've defined outliers. We've talked about what they are. Talked about how they could be statistical, could just be distributional. It could be that they're qualitatively outliers. They don't belong there because they're not part of that population. Great. What do we do? All right, we've identified them. Now we have them in our data set or something. What do we do with them? Well, there's a couple things you can do, a couple different ways of thinking about it. So once you find them, you can look into the case to see if there are indicators that the case is not part of your intended sample. If this is true, then just delete the case. So if a score seems like it's wildly outside of what you're looking at distributionally, then check out what's going on with it. Maybe there was someone slipped by. I remember a long time ago, as an undergraduate, we were doing a study using the Stroop task, and a friend of mine was running the study, and I was helping him, and we were running everybody. Everyone was going fine. It was going great. We got this one participant that took, when everyone else was taking like 10 minutes, he took like an hour and a half to go through the time. Like it was like just a crazy amount of time. And come to find out afterwards, and we were sort of asking him some questions and stuff because we didn't have any screeners that would pick it up. He had some reading or some kind of disorder that made it hard to read. I think he was like extremely dyslexic or something. So he was slowed down not by the color problem, not the part of where he's having trouble reading the problem. It was more of a learning or this really something. So it just took him forever to process all the stuff. So he took way, way long. And we realized that he was not, we wanted sort of quote unquote normal participants, with no reading disabilities, no, color blindness, those kind of things. So we ended up leaving him out of the analysis because he didn't seem to fit with all the other students that we were looking at. So that's just an example that sometimes when you look a little deeper, you can figure out, oh, that's why this person's so different. It's because these other qualities about them sort of make them not part of the sample. So you're either going to figure that out and delete the case, or you can try to reduce the influence of the outlier. Now, this one's a little bit more out there in terms of approach, but it is done and it actually makes some sense once you get past the initial knee-jerk, like, wait, you're changing scores. So if you have an extreme value, an outlier that's sort of disconnected, well, what makes them disconnected is the sort of space between them and the other scores. So why not just move their score in? Change their score so it's still the extreme score, but not as extreme anymore. You move them in so that they're now next to the next highest person and reduce their influence down somewhat. Now that works, thinking univariately, you can look at the distribution, sort of move them in, but you also got to think about it if it's part of your regression line, the influence and caused by the discrepancy and the leverage, you may have to sort of move it, in a couple different ways, depending on how it works. But let's think just, sort of univariately, you might be able just to move it in. And so it's a controversial approach, but it's recommended by Tabachnik and Fidel in their textbook, and something you might see people do, because especially if you're doing something where it takes a lot of time and effort to run people through things, run people through, examples, or you're having someone go through an experiment, it takes a long time, you may not want to throw out their score because you spend a lot of time and effort collecting their data. So why not just leave it and just reduce the influence their score has?